Welcome back. In this video, our goal is to talk about how to do questions where you're given a graph of some function, like this one for f of x, and we're asked to sketch what the graph of the derivative looks like. Now, when you go about doing this, I recommend putting a set of axes to draw the graph of the derivative on immediately below the graph whose derivative you're sketching. Here's why. The thing that is actually the same between the original function and the derivative is the inputs. That is the x-axis. And so if I line them up like this vertically, then this point, say, on the x-axis corresponds to the point immediately below it on the graph below. I don't actually recommend drawing the graph of the derivative and the original function superimposed on each other, which we did in the last video. One, it makes it more confusing because you're tempted to think about when the graphs intersect. But really, actually, the output of the function and the output of the derivative are very different kinds of things. The function is giving you values, but the derivative is giving you slopes. So as much as it makes for fun exercises like we did in the last video, usually it's best to look at the graph of the function and the graph of the derivative on separate axes. So, how do we start a question like this? The first thing you want to do is you want to look for spots where the derivative is 0. Namely, that would be this spot, where the tangent line is horizontal, and this spot, where the tangent line is horizontal. And these 2 points where the tangent line is horizontal are going to correspond to 2 points down here on the graph of the derivative where the derivative is 0. That is where the graph of the derivative crosses the x-axis. So those 2 points, those are on the graph of our derivative. So in doing this, I've created these dashed lines. And the dashed lines are here basically to talk about how we've broken the original graph into 3 pieces, or 3 zones, if you will. And I want as my next step to think for each of these pieces whether the derivative is going to be positive or negative in that piece. So in other words, if I look at just this piece of the graph, is the derivative positive or negative? Well, if I drew in a tangent line at any point on here, it would look something like that, and that has a negative slope. So everywhere in this zone, this first piece, the derivative is going to be negative. That is to say, the graph of the derivative is going to live down here in this corner. It's not going to touch this piece at all. Okay, what about this next section? Well, everywhere in here, the slope of the tangent line is positive. The tangent lines lean in this direction. Okay, and so everywhere in this piece, the second piece, the derivative is going to be positive. Which means that between these 2 dashed lines, the entire graph is going to live up here, and it's not at all going to enter this piece down here. Finally, for this last piece, again, the slopes of the tangent line are negative, and so the derivative is negative. And so I should fill in that here I'm going to have things being negative. So the graph, when I actually fill it in, is going to live entirely in this space. And so nothing is going to show up in this space. This actually gives me a lot of information about what the graph is going to look like. It's got to start down here somehow, and then journey upwards into here, and then journey back downwards into here. And that already sort of starts to fill in my sense of what the graph is going to look like. So let's look at what's happening to the slope over this piece. Okay. The slope I know is negative over this whole piece, but my question is the slope getting more negative or less negative over this piece? And what I can see is on the left, the tangent lines are steeper. On the right piece of this purple part of the graph, the tangent lines are shallower. So the slope here is actually getting less steep. Okay. And so what that means is that my graph has to sort of be coming up through this piece. Okay. And remember, as my graph comes up through this piece, it has to end at this point. I have no choice. This point's on the graph. So I can draw something like that. And we don't have to worry about anything about how this line is bending or anything like that. Just the fact that this line is increasing, that's plenty. Here in the middle, what happens? Well, initially, our tangent line has slope 0. Then it becomes slightly positive, more positive, more positive. But then it actually starts shallowing out again. So it's a little less positive, and then becomes 0 again. Okay. Again, this is about the steepness of the line. So the tangent line starts out having this slope, then gets steeper, until somewhere in the middle, the tangent line has that slope. But then from there, it flattens out again until at this second horizontal dashed line, the tangent line has slope 0 again. And so what I just described is that the slope does something like that. So the slope gets bigger for a bit and then smaller. Let's look at the last piece here. The slope starts off being 0, then becomes steeper, steeper, steeper. But actually, if you follow along somewhere along and about there, it actually gets the steepest it's going to get, and then it actually starts to shallow out again. And so the derivative here goes from being 0 to being slightly negative, more negative, more negative, but then it starts getting less negative, less negative, less negative. It's always staying negative, but it's actually becoming less and less negative as we go over. And so here's the part where it's becoming more negative, up until about here. Then it turns around and the slope starts becoming less negative until the slope is becoming very, very, very shallow, like that, but still negative. And so the graph of our derivative ends up looking something like this. Now, all of this has been about positive slope, positive derivative, negative derivative. I want to connect this back to words we used back in chapter 1, namely, negative derivative just corresponds to the spot where the function is decreasing. Positive derivative corresponds to the spots where the function is increasing. And so really what happened here, originally our function was decreasing, so the derivative was negative. Then our function was increasing, so the derivative was positive. Then our function was decreasing again, so the derivative was negative. That's basically where all of these things came from, all of these. Here's our function g of x, whose graph is a parabola. And I want to give you one tip before we go any further, which is that the derivative of a parabola is always a line. So for parabolas, we can actually probably do our best work in terms of figuring out what the graph of the derivative is supposed to look like. Okay, so again, first step, find where the derivative is 0. The derivative here is 0 at the vertex. Trace that point down to the graph that you're going to make your graph of the derivative. Okay, and that gives you a point on the graph of the derivative. Hooray. Okay. Now, we have to look at the graph and decide whether the derivative is positive or negative in each of these sectors. Here, there's only 2 sectors. So the left one and the right one. In the left sector, this function is increasing. It has positively sloped tangent lines. And so in that piece, the derivative is positive. Over here, the function is decreasing. It has negatively sloped tangent lines. And so the derivative is negative. Now, actually, with the tip, because if I'm looking at a parabola, the answer is always going to be a line, I basically don't have any more choices. I have to draw a line that is positive here and negative here. It's got to end up looking something like this, because it has to pass through this point. And then, ta-da, that's my graph of G prime. Here's my function f of x now. Now this looks not so different from a minimalist impression of the parabola whose graph we just drew. And so you might think that the derivative of this is going to look a lot like the derivative that we just did. But as it turns out, it's not. And there's a couple reasons for that. One reason is that at the quote-unquote vertex here, or as I'm going to call it, the corner, this function actually doesn't have a derivative. And that maybe seems weird, but why is it that it doesn't have a derivative? It doesn't have a derivative because there's no correct choice for a tangent line. The tangent line, remember, when I try and draw it, is supposed to go in the same direction as the graph, but if I try and draw this line as the tangent line, well, that only goes in the direction on the left. If I try and do it over here, it only goes in that direction on the right. And if I try and split the baby and do a horizontal tangent line, well, then it doesn't actually agree with the direction of the function anywhere. So really what's happening here is a lot like what happened when we talked before about functions that did this kind of thing, where there was a jump discontinuity, and basically what was happening was there was this sort of line in the middle of the function where the left piece and the right piece looked like they came from different functions. They did not agree with each other. Okay. The same thing is really happening in this graph at this point. If someone only showed you the left half and asked you to guess how the function went, you would be very confident in saying, okay, well, it must be a line. Or, if someone only showed you the right half, you would likewise be very confident, okay, it must be a line. But instead, here the function has radically changed direction. And even though it's still continuous, because the left and the right pieces actually line up, their slopes don't. And so I get this fact that this thing doesn't have a derivative. And what that means is that when I go to draw the graph of the derivative down here, I'm just going to get nothing on the graph of the derivative at this point. So I'm still going to look at the left and look at the right pieces and draw what the derivative looks like there. But at this point on the graph of the derivative, there's going to be no point. There's going to be holes. Okay, now let's look to the left of the dashed line. Is the derivative here positive or negative? Okay, well, it's positive. And then over here, it's negative. Okay, again, increasing positive derivative, decreasing negative derivative. And so now I have to think about, well, how do I draw this graph? I know it's going to live entirely up in this corner and down in this corner, but what's it going to look like? Is it going to be veering in like that, or what exactly is going to happen? And how we decide that is dictated by how the derivative is changing as I move along this line. As I move along these 4 points, is the derivative getting bigger or smaller? And the actual answer is that the tangent line at all of these points is the line itself. Because again, in this left-hand universe, the graph of f is just a line, And so the tangent line, or the line that goes in the same direction as the line, is actually the line itself. And so the derivative of this function everywhere is just the slope of this line. And so that means that in fact the derivative is actually a constant positive number over here. So the derivative graph looks like this, just a flat line. And all these same words are true over here, except the derivative is negative. And to indicate that the function did not have a derivative at this spot, I'm going to put in an open circle here and here to say, hey, if you try and find the derivative at this exact point, it just doesn't work. Okay, so here we have a new function. And often when I give you a function that's sort of made out of pieces like this, I'll even explicitly say, this piece, the graph is a line. This piece, the graph is a parabola. And this piece over here, the graph is a line again. And I'm really telling you these things so that you can use the facts that we know, which include the derivative of a parabola is a line. And also, as we learned in the last example, the derivative of a line is a horizontal line. Okay, so I am going to tackle this a piece at a time. I'm going to look at the parabola first. Note there's a spot in here in the middle where the derivative is 0. So that spot is on the graph of the derivative. And we can add yet another dividing line here. In this piece, the derivative is negative. And over here, the derivative is positive. So that must mean, since this is a line, it must look something like this. Okay, that's the middle piece. Now I want to look at the right-hand piece. And so on the right-hand piece, this is a line. The slope is positive. Okay. And so I need to draw a horizontal line here. And that horizontal line needs to be above the axis. But really, there are 3 places I could draw that line. I could draw it down here below this. I could draw it exactly equal with this. Or I could draw it up here above that. Which of those 3 is right? Well, remember, this graph here is telling you the slope of the parabola at that point. So really, I'm asking, if I look at the slope of the parabola at this point, which is that, is this slope bigger or smaller than that? And it's considerably smaller. And so when I go to draw in this, I need to make sure, actually, that my horizontal line is a good deal lower than where I left off my graph of the parabola. And in particular, that means this is a corner. It's a place where the function changes direction. And so that means I'm going to have open circles on my graph of my derivative. These are supposed to be on top of each other, even though they're not. And so this is a spot where the derivative is undefined. Everywhere else, the derivative is fine. Now, I have to play the same game over on the left. I have a line whose graph is going to be a horizontal line. It's going to be a horizontal line of negative slope. And I have to match that line up with the parabola. And so the question is, at this point where these 2 graphs join, is the slope of this line bigger than the slope of the parabola at that point? Is it less than the slope of the parabola? Or is it exactly the same? And to the best of our ability to determine it, it actually looks like it's exactly the same. Which means that this graph should actually pick up exactly where this graph left off. And so my graph should look like that. And so there is a closed circle here indicating that there really is a derivative at this point. And so my derivative graph will end up looking like this. There's just one more special case I wanted to talk about. And that is the case where we have a semicircle. So I'll draw my best attempt at a semicircle. It's actually not a bad attempt. I'll take it. Okay, and I want to try and draw the derivative. The derivative is 0 at this point, where the tangent line is horizontal. The derivative is positive over in this universe, and negative over in this universe. And I'll note the function actually ends at this point. So when the function's graph ends, that's definitely a sign that the derivative also ends. I can't draw a tangent line to a graph that doesn't exist. So I need to make sure my graph of my derivative stops here and stops there. But what's interesting about this graph of a circle, that's something that hasn't come up in any of the previous examples, is that if I look at the endpoint of this circle, what is the tangent line? Well, the tangent line is actually vertical. Here too. What's the slope of a vertical line? Well, it's either undefined or infinite based on your philosophy. But what this is actually going to do in terms of the graph is, if I look as I go closer and closer and closer to here, the line is actually getting steeper and steeper and steeper and steeper, and the end point is actually that it's vertical. And so the slope across this piece, it actually runs all the way up to positive infinity. And so what that means is that on the graph of the derivative, there's actually a vertical asymptote here. And in exactly the same way, over on this piece, as I run from here over to here, the line goes from being flat to being steeper and steeper and steeper and steeper until eventually it's infinitely steep. And so the derivative continues on, and I get a vertical asymptote over here. And so even though circles are a fairly friendly and innocuous seeming object, when you draw the derivative of one, you actually end up with this sort of complicated looking thing with these sorts of asymptotes. All right. I'm going to wrap up here and remind you that we have test 4 on Friday, October 30th, and it covers these 4 sections, which are all about derivatives. Okay, so this section was about calculating the derivative at a point using a limit. This section was about tangent lines and finding equations of tangent lines and all of that sort of business. This was about finding the derivative as a function. So this was like f prime of 4. This was like f prime of x. And this is the section we've just finished on sketching graphs of the derivative from graphs of the original function, or identifying which graph is the derivative out of a pile of graphs, that sort of thing. All right. So that's all for now. I'll see you next week.